Welcome to my 60th tutoring session in A-level chemistry. In this video, I'll give a detailed explanation about some of the important parameters related to UV visible spectroscopy. I'll explain the chromophore, types of chromophore, and its significance. I'll also explain the importance of chromophore, the influence of Auxochrome on λmax, and the color of the compound, and also the effect of pH on the Auxochrome. And finally, I'll add a brief note on the CHROMOGEN and the role it plays in qualitative and quantitative analysis. Now the word chromophore, it is derived from the Greek word chroma, refers to color, and phore means to bear. So chromophore is a Greek word meaning color bearing groups that impart color to the molecule. Now chromophores are covalently unsaturated with groups like carbon-carbon double bond, usually seen in alkenes or aromatic compounds like benzene. Other examples of chromophores are covalently unsaturated carbonyl groups, azo group, and nitro groups. There are two different types of chromophores. One is the independent chromophore, the other is the conjugated chromophore. Now the independent chromophores are responsible for the color of the compound. And some of the examples of independent chromophores are nitro group, azo group, and carbonyl group. So let me mention some of the examples. Now both phenol and aniline, they are colorless in nature, while para-nitroaniline and para-nitrophenol, they are bright yellow colored compounds. So this is because of the presence of the independent chromophore, that is the nitro group. So the independent chromophores like nitro group, they are solely responsible for the color of the compound. Here's one more example indicating the importance of the independent chromophore. Now in case of azo dyes like azobenzene and para-hydroxyazobenzene, you see the azo groups, and the azo group, it is linking the benzene chromophores together, leading to extension of the chromophore. Now both azobenzene and para-hydroxyazobenzene, they are colored compounds, but both differ structurally as well as in the intensity of the color of the compound. Azobenzene is light red in color, while para-hydroxyazobenzene is bright red color. Now the azo group, it not only links the chromophores together, in this case it is linking the two benzene rings, it also leads to extension of the conjugated system. So the azo group, it links both the chromophores, both the benzene ring, in case of azobenzene and para-hydroxyazobenzene, and that leads to extension of the conjugated system. So whenever there is extension of the conjugated system, it leads to a colored compound. Now in case of para-hydroxyazobenzene, the hydroxy group is present at the para position as an auxochrome, and auxochrome, it does not have a characteristic absorption of its own, but it can modify the absorption of the chromophore. And the presence of hydroxy group leads to further extension of the chromophore, and that leads to further intensifying the color of the compound. And that is why para-hydroxyazobenzene is bright red in color, while azobenzene without the auxochrome is light red in color. Now the second type of chromophore is the conjugated chromophore. Now, what is conjugation? Now, conjugation is nothing but alternative presence of single and double bond. Now, this type of conjugation, that is the presence of alternative single and double bond, can be seen in aromatic compounds like benzene and its polycyclic derivatives like naphthalene, anthracene, and phenanthrene. Now, in case of benzene, you find three alternative double bonds arranged in a cyclic manner, and the double bonds are alternatively arranged. So in case of naphthalene, you can see the two benzene rings are fused together at the ortho positions, and here you can see the extension of the conjugation. So in aromatic system, that is in the benzene ring, there are three alternative double bonds arranged in a cyclic manner, but in case of naphthalene, there is extension of conjugation, and this leads to shift in lambda max from 255 nanometers to 286 nanometers. So the shift in lambda max from 255 nanometers to 286 nanometers is due to extension of the conjugation. Now, when you find the extension of conjugation in the molecule, it definitely affects the wavelength of light being absorbed. You can also find the conjugation in open chain compounds like 1,3-butadiene and highly conjugated system like beta carotene. Now, beta carotene is a colored pigment present in carrots, and they absorb at a specific wavelength of 453 nanometers. Now, in case of 1,3-butadiene, it absorbs the radiation at 223 nanometers, while in case of beta carotene, you can see the wavelength is shifted. There's a drastic shift in the lambda max from 223 nanometers to 453 nanometers. This is due to extension of the conjugated system. So there are nearly 11 double bonds in case of beta carotene that are alternatively arranged, resulting in conjugation. So whenever there is extension of conjugation, there is bathochromic shift. That is, there is shift in the lambda max towards longer wavelength. And this conjugation definitely affects the wavelength of light that is being absorbed by the chemical. Now, when the electromagnetic radiation, when it strikes the molecule, it interacts with the chromophores, and the electrons present in the chromophores, usually the pi electrons as well as the non-bonded electrons, they absorb the radiation, and they absorb the radiation at a specific wavelength depending on the type of the chromophore that is involved in the structure, and the unabsorbed radiation is reflected, and when the unabsorbed reflected light, when it strikes the retina of the eye, it gives a characteristic color as seen by the observer. So benzene, naphthalene and 1,3-butadiene, they absorb in the high energy UV region, and hence they are colorless. While beta carotene, due to the extensive conjugated system in the molecule, it absorbs in the low energy visible region, and therefore they are colored. So definitely there is effect of conjugation on the chromophores. So extended conjugation shifts the absorption to longer wavelengths. That is, you find the bathochromic or the red shift. So whenever there is extended conjugation, you will find that radiation is absorbed at longer wavelengths, which is of lower energy. Now, what is UV visible spectroscopy? Now, UV visible spectroscopy is a scientific study that involves the interaction of UV radiation or the visible radiation with the molecule. And the molecule under study, it can absorb either the UV radiation or the visible radiation, and that depends on the type of the chromophore present in the molecule under analysis. An outcome of this interaction is absorption of radiation of a particular wavelength. Now the visible region ranges from 400 to 800 nanometers, while the ultraviolet region ranges from 200 to 400 nanometers. Now there are two contrasting features between the UV region and the visible region. The first contrasting feature is the wavelength. As you can see in this picture, now the visible region has a longer wavelength, while the ultraviolet region has a shorter wavelength. And the second contrasting feature is the energy. Ultraviolet region is high in energy, while the visible region is low in energy. So the two contrasting features are the wavelength as well as the energy. And these two parameters are inversely proportional to each other. So when the wavelength increases, energy decreases, and when the wavelength decreases, energy increases. And this plays a vital role in absorption of a particular wavelength of radiation by the molecule under analysis. Now chromophores, as I already mentioned, are covalently unsaturated groups. And when the radiation strikes the molecules bearing these chromophores, a specific wavelength of light, it could be a UV region or wavelength in the visible region, and the unabsorbed radiation is reflected back, and when it strikes the retina of the eye, it is seen as a characteristic color as seen by the observer. Now, when do you think the energy will be absorbed by the molecule? When the radiation with a certain amount of energy strikes the molecule with a characteristic chromophore. Now the electrons present in the chromophore, they absorb the energy and undergo transition from the ground state to the excited state. Now when will the energy be absorbed? The energy striking the molecule in the form of radiation will be absorbed when the difference in energy between the excited state and the ground state is equal to the energy of the electromagnetic radiation striking the molecule. So only then the energy will be absorbed, not otherwise. So when the difference in energy between the excited state and the ground state, when it is not equal to the energy of the incoming radiation striking the molecule, the energy will not be absorbed. So energy has to be matched. So whenever the energy does not match, there will be no absorption. So in case of highly colored azodite compound, that is phenylazo-beta-naphthol, when the radiation strikes the molecule, the loosely held pi and the non-bonded electrons absorb the electromagnetic radiation, undergo transition from the ground state to the excited state, and the unabsorbed radiation is reflected back and is seen by the observer as a red colored light because of the wavelength of that particular radiation, which is reflected back, striking the retina of the eye. And that is why phenylazo-beta-naphthol is a red colored dye and it absorbs in the visible region. And why it absorbs in the visible region? Because of its low energy. So energy in the visible region is more than sufficient to cause electronic transitions or to cause excitation of electrons that are loosely held. So in the azo group, you can see there are two types of electrons. One is the loosely held pi electron, other is the very loosely held non-bonding electrons. So the energy in the visible region is more than sufficient to bring about excitation of these two electrons present in the azo group. And the unabsorbed wavelength, which is in the red region, which is reflected back and is seen by the observer. And that is why phenylisobutadiene is a red colored compound because the wavelength that is reflected back is red in color. Now each color is associated with a certain amount of wavelength and energy. And that is why rainbow has 7 distinctive colors, because each color in the rainbow is associated with different wavelength and energy. Now acetone is a carbonyl compound. It absorbs in the UV region and hence it is colorless. And when the radiation strikes the chromophore present in the acetone molecule, so the chromophore in case of acetone molecule is the carbonyl group. When it interacts with the incoming radiation, it brings about electronic transitions of the pi electron as well as the non-bonding electrons present on the oxygen atom. So acetone is colorless because it absorbs in the UV region, while phenylisobutadiene is highly colored because it absorbs in the visible region. Now the energy of the electromagnetic radiation is given by the equation E is equal to h mu, where E stands for the energy of the electromagnetic radiation, h is the Planck's constant, and mu is the frequency of the radiation. Now you can see in the equation that energy and wavelength are inversely proportional. When the energy decreases, wavelength increases, and when energy increases, the wavelength decreases. Now as seen in the diagram depicting the UV region and visible region, you can see in the visible region the wavelength increases but energy decreases, while in the UV region wavelength decreases, energy increases. So wavelength and energy, they are inversely proportional. Now in case of the azo dye, that is phenylisobutadiene, the molecule is associated with 3 different chromophores. Now chromophore 1 is the benzene ring, the second chromophore is the azo group, and the third chromophore is the naphthalene ring. Now you also find a auxochrome, that is hydroxy group, that is covalently bonded to the second position of the naphthalene ring, while the azo group is covalently bonded to the first position of the naphthalene ring. Now the azo group, it has 2 types of electrons. One is the loosely held pi electrons and the other is the very loosely held non-bonding electrons. Now these loosely held pi as well as the very loosely held non-bonding electrons, when it interacts with the incoming radiation, it absorbs the electromagnetic radiation, and because of the loosely held nature of this electrons, as the electrons are loosely held, very less energy is required, and therefore energy is absorbed in the visible region, and therefore the molecule absorbs at longer wavelength in the visible region because they have very less energy, and that is more than sufficient to bring about excitation of these 2 electrons and bring about the transition from the ground state to the excited state. And the unabsorbed wavelength of light, when it strikes the retina of the eye, it is seen as a characteristic color by the observer. Now in the azo group, you find 2 nitrogen atoms held together by a double bond, and you also find a lone pair of electron on both the nitrogen atoms. Now the sigma bond is depicted as a red line, while the pi bond is depicted as a purple line, with both the nitrogen atoms having lone pair of electrons. Now here's the orbital diagram of the azo group at the ground state, and the pi molecular orbital or the pi bonding orbital is depicted in purple color with pi electrons, and the anti-bonding orbital is depicted in red color represented by pi star, while the non-bonding electrons is highlighted in yellow color. That belongs to the nitrogen atom. Now when the radiation strikes the azo group present in the molecule, the electrons absorb the energy and they jump from the bonding orbital to the anti-bonding orbital, bring about two types of transition. One is N to pi transition and the other is pi to pi transition. So you find two types of transitions when the radiation strikes the azo group. One is the transition from the pi bonding orbital to the pi star anti-bonding orbital, and the other is the N to pi transition. And these two transitions plays a vital role in absorption of longer wavelength in the visible region. So phenylazobate and naphthol is red colored. It absorbs in the visible region. Reason being, the energy in the visible region is more than sufficient to bring about excitation of this pi electron as well as non-bonding electrons. And the unabsorbed reflected light is seen by the observer as a red colored compound. So carbonyl group present in acetone, radiation strikes the molecule, bring about or inducing electronic transitions in the pi electron as well as in the non-bonding electrons. And therefore acetone absorbs in the UV region. So here's a diagram depicting the electronic transitions brought about by interaction of the radiation with the carbonyl group of acetone molecule. Again, two types of interactions. One is pi-pi transition, other is the N to pi transition. Now therefore, colorless compounds absorb radiation in the high energy UV region ranging from 200 to 400 nanometers, while the colored compounds absorb radiation in the low energy visible region ranging from 400 to 800 nanometers. Now let's talk about the auxochrome. Now auxochrome is a saturated group or a substituent with non-bonding electrons, and they do not have characteristic absorption of their own, but they can modify the absorption of a chromophore. That is, when the auxochrome is attached to a chromophore, it can modify the absorption of the radiation by the chromophore. So it can influence both the intensity of radiation that is being absorbed as well as the wavelength of radiation that is being absorbed by the chromophore. And some of the regularly encountered auxochromes are hydroxy group, amino group, and halo group. And these substituents or auxochromes are present in heteroatoms like oxygen, nitrogen, and halogen, as in case of hydroxy group, amino group, and halo group, with lone pair of electrons on them. So they have at least one lone pair of electron, as in case of nitrogen atom present in amino group, and two lone pair of electrons in oxygen atom as seen in hydroxy group, and you find three lone pair of electrons in halo group like bromine and chlorine. And these auxochromes also play a crucial role in extending the conjugation. So extension of conjugation is another role played by the auxochromes, and therefore modify both the wavelength and intensity of absorption. Now let's see how the auxochrome interacts with the benzene chromophore, and also how the auxochrome influences the lambda max, and how the pH has its effect on the auxochrome. Now phenol, it has a hydroxy group covalently linked to the benzene ring. It has a lambda max of 270 nanometers. The auxochrome in case of phenol is hydroxy OH group, where you find two lone pair of electrons on the oxygen atom. Now in acidic medium, That is when phenol is dissolved in acidic medium like 0.1 molar HCl. The oxygen atom has two lone pair of non-bonding electrons. Now let's see what structural change happens to phenol or the hydroxy group under basic conditions. When you try and dissolve phenol in alkaline medium, like say we dissolve the phenolic compound or the phenol in 0.1 molar sodium hydroxide, we see that oxygen has three lone pair of non-bonding electrons. Because when you dissolve phenol in sodium hydroxide, it undergoes ionization, resulting in formation of phenoxide ion. An hydrogen atom that was covalently bonded to hydrogen atom, it is removed in the form of proton and exposing the oxygen atom with three lone pair of electrons. So in acidic medium, you find two lone pair of electrons associated with the oxygen atom, while in alkaline medium, you find three lone pair of electrons associated with the oxygen atom. And this is the reason why there is shift in the lambda max from 270 nanometers that you find in phenol in acidic medium to 287 nanometers under alkaline medium. So this explains the fact that more the number of electrons available, more will be the conjugation resulted. And these lone pair of electrons on the oxygen atom interacts with the benzene chromophore by resonance. And what about aniline? Now aniline structure, you find the amino group covalently bonded to the benzene ring with lone pair of electron present on the nitrogen atom. So the auxochrome amino group, in case of aniline, it interacts with the benzene chromophore by resonance, where you find the lone pair of electron is delocalized into the ring. So in alkaline medium, when you dissolve aniline in 0.1 molar sodium hydroxide, so nitrogen atom has one lone pair of non-bonding electrons. While in acidic medium, like 0.1 molar HCl, you find the amino group is protonated under acidic medium. And after protonation, the lone pair of electron that was present on the nitrogen atom is no longer available for conjugation. And thereby you see the lambda max drastically reduces. So when you dissolve aniline in acidic medium and measure its absorbance, you find that the lambda max falls or decreases from 286 nanometers to 203 nanometers. This is because of non-availability of lone pair of electrons on the nitrogen atom, which happens due to protonation under acidic conditions. And another auxochrome, which is less encountered, is the halo group, which could be either chlorine atom or bromine atom. Now the mechanism involved during the interaction of the auxochrome with the chromophore benzene system is by n-pi conjugation, where you find the hyperconjugation between the non-bonded electrons on the nitrogen atom in case of the amino group in aniline and the pi system of the benzene ring. And this n-pi conjugation or the hyperconjugation between the non-bonded electrons on the nitrogen atom and the pi system of the benzene ring, it happens by resonance. And this is how it happens. Now the lone pair of electron on the nitrogen atom, it is getting delocalized into the ring by resonance. And as a result, you can see there is extension of conjugation. And this extension of conjugation shifts the lambda max. And under acidic condition, when the amino group is getting protonated, you can see that there is drastic fall in the lambda max from 286 nanometers to 203 nanometers. So auxochromes basically, they do not have a characteristic absorption of their own, but they can modify the absorption of a chromophore by extension of the conjugation. So auxochrome basically modifies the absorption of radiation by the chromophore by extending the conjugation. That is by extension of conjugation, and thereby it modifies both the wavelength and intensity of absorption. Now let's see how the lambda max of benzene changes due to different types of auxochromes attached to the benzene chromophore. So here's a UV absorption spectra depicting the effect of auxochrome and n-pi conjugation on the lambda max of substituted benzene rings. In case of benzene ring, the lambda max is 255 nanometers. So what is lambda max? Lambda max is the wavelength where you find the maximum absorption of radiation by the molecule. Now in case of chlorobenzene, the auxochrome is the chlorine atom covalently bonded to the benzene ring. Lambda max is 265 nanometers. And in case of phenol, auxochrome is OH group and the wavelength at which it absorbs the radiation is 270 nanometers. Well, in case of aniline, auxochrome is amino group with lone pair of electrons. Its lambda max is 280 nanometers. So the chromophore is common for all these 4 compounds. So benzene is the common chromophore for all the compounds, but the auxochrome is different. So auxochrome is chlorine in case of chlorobenzene, hydroxy group in case of phenol, and amino group in case of aniline. So you can see that there is varying effect on the lambda max. And this happens due to n-pi conjugation. That is due to hyperconjugation between the non-bond electrons on the heteroatom and the pi system of the benzene ring. So definitely the auxochromes have varying effect on the lambda max of benzene. So in case of chlorobenzene, the lambda max shoots from 255 to 265 nanometers. Well, in case of phenol, you can see the lambda max shifts from 255 nanometers to 270 nanometers. And this is due to n-pi conjugation. That is due to hyperconjugation between the non-bonding electrons on the pi system of the benzene ring. Now let's see how the color of the compound is influenced due to the presence of chromophore and auxochrome. Now benzene, phenol and aniline, all 3 are colorless with their respective lambda max values. So in case of phenol, lambda max changes from 255 to 270, and in case of aniline, lambda max changes from 255 to 286. And the mechanism we have just discussed about that. So how there is a shift in the lambda max towards longer wavelength due to n-pi conjugation. But when you introduce a nitro group to the phenol and aniline at the para position, you can see that the compounds have become highly colored. So both para-nitroaniline and para-nitrophenol, they are bright yellow colored compounds. So why phenol and aniline, they are colorless despite the presence of the auxochrome OH and NH2 is because the extension of the conjugation is not sufficient enough to bring about absorption in the visible region. The moment nitro group is introduced to the para position, there is extension of conjugation, and this extension of conjugation shifts the lambda max towards longer wavelength, making the molecule to absorb in the visible region. So the presence of chromophore do not guarantee the color of the compound. So you cannot just take it for granted that chromophore is present and therefore the color should be, compound should be colored. Or just because the auxochrome is linked to the chromophore in the molecule, the compound has to be colored. So it doesn't work that way. So it all depends on the extension of conjugation. More the conjugation, the absorption will be shifted towards the longer wavelength, leading to bathochromic shift, and that results in the compound to be colored. So to make a substance colored, the chromophore has to be conjugated with an extensive system of alternative single and double bonds as seen in aromatic rings. So auxochromes like OH and NH2, it just extends the conjugation. And in some case, it deepens the color by extending the conjugated system between the chromophore and the auxochrome by resonance. And the mechanism for extension of conjugation by the auxochromes will be discussed later in the video. And in case of azobenzene and para-hydroxyazobenzene, the major chromophore is the azo group, and this we have dealt in detail. So auxochromes do not have characteristic absorption of their own, but they can modify the absorption of radiation by the chromophore and intensify the color. So this is clearly highlighted in case of para-hydroxyazobenzene. So in case of para-hydroxyazobenzene, the hydroxy group is present para to the azo group, and this leads to extension of conjugation. And it intensifies the color of para-hydroxyazobenzene. So azobenzene is light red in color, while para-hydroxyazobenzene is bright red in color. Now I want my viewers to focus their attention on these three arrows here, representing the three different scenarios. So all these three scenarios, they arise with respect to the benzene ring. Now in first scenario, so benzene has a lambda max of 255 nanometers, and you see there is increase in the lambda max when there is substitution of hydrogen atom in the benzene ring with auxochromes, as you've already seen in case of chlorobenzene, phenol and aniline, and the mechanism that is involved. And in the second scenario, you see the substitution of hydrogen atom in benzene ring with independent chromophores like cyano group and carboxyl group, resulting in only extension of the chromophore. So cyanobenzene and benzoic acid, they are colorless compounds. So all you can see is that there is extension of the chromophore, and this extension of chromophore results in increase in lambda max. Now two things can happen here. One is presence of auxochromes or additional chromophores can lead to extension of chromophore. And second thing that can happen is when the extension of chromophore is more, that may result in the compound to be colored because there is shift in the lambda max, which makes the compound, whenever there is more extension of conjugation, it makes the molecule to absorb in the visible region. So when you see a colored compound, it means that that compound absorbs in the visible region. And third scenario, you see the substitution of hydrogen atom in the benzene ring with auxochrome, and that leads to extension of the chromophore, as in case of para-aminobenzoic acid, para-hydroxybenzoic acid, para-nitrophenol and para-nitroaniline. Now aniline and phenol are colorless. Aniline has a lambda max of 286 nanometers, while phenol has a lambda max of 270 nanometers. So both are colorless, but when you introduce a independent chromophore like nitro group at the para position, you can see that the lambda max jumps. So the drastic increase in the lambda max. So in case of phenol, there is increase from 286 nanometers to 380 nanometers, while in case of phenol, due to the nitro group, the lambda max increased from 270 to 380 nanometers. And this because of extension of conjugation and chromophore through the benzene ring, and this caused by resonance. And the mechanism is depicted here, where you can see the lone pair of electron on nitrogen atom in case of para-nitroaniline that is being delocalized into the ring, resulting in extension of conjugation that is caused by resonance. And same mechanism holds good even in case of para-nitrophenol, where the two lone pair of electrons on the oxygen atom is delocalized into the ring by resonance, resulting in extension of conjugation. So always remember, whenever there is extension of conjugation or the chromophore through the benzene ring brought about by resonance, two things will happen. One is shift in the lambda max towards longer wavelength, that is redshift or Batha-chroma shift will happen. The other thing that will probably happen is the compound may be colored because the compound will absorb in the visible region. So whenever you see a colored compound, take it for granted the colored compound absorbs in the visible region. So auxochromes like OH and NH2 deepens the color by extending the conjugate system between the chromophore and the auxochrome by resonance. Now let's see what happens. Now here in case of para-nitroaniline and para-nitrophenol, you see a shift in lambda max, and the introduced nitro group is at the para position. Now let's shift the position of the nitro group from the para position to the ortho position and see what happens to the lambda max. So when you shift the nitro group to the ortho position, you can see that there is no change in lambda max. The lambda max almost remains the same. This is because when the groups are ortho to each other, there is no extension of conjugation or the extension of chromophore through the benzene ring. And whenever there is extension of conjugation by resonance, the lambda max increases. You see a bathochromic shift. And when the groups are ortho to each other, you can see that there is no extension of conjugation. And therefore, there is no change in lambda max or increase in lambda max. And only when the groups are para to each other and when they are complementary to each other, you see a shift in the lambda max, or you see a bathochromic shift in the lambda max towards longer wavelength. Now coming to the last part of the discussion, that is chromogen. Now what is a chromogen? Now chromogen is a chemical or a reagent that produces a color or a chromophore by a chemical reaction. And a chromogen is employed for identification purpose. That is, it can be used for qualitative evaluation, and most of the case it's used for quantitative analysis of different types of phenols. Now both benzoic acid and salicylic acid are colorless with lambda max of 230 nanometers and 237 nanometers. Now in case of benzoic acid, the carboxyl group is covalently bonded to the benzene ring, and in case of salicylic acid, the carboxyl group as well as the hydroxyl group are ortho to each other. And I just mentioned that whenever the groups are para to each other, there will be extensive conjugation. That is, when the groups are para to each other, there will be extension of conjugation, and when the groups are ortho to each other, there will be no extension of conjugation and there will be no change in lambda max. So that is exactly what has happened here in this case. Despite the OH group being auxochrome, so OH is an auxochrome. So despite the presence of the auxochrome like OH in case of salicylic acid, there is no change in lambda max. That is because there is no extension of conjugation. So the placement of the auxochrome in the benzene ring is also crucial. Now, these colorless compounds can also be estimated in the visible region by using chromogen. Now, chromogen is a chemical or reagent that develops a color or a chromophore by forming a complex. Now, for example, you can estimate salicylic acid by treating with ferric chloride reagent, and on treating with ferric chloride reagent, the salicylic acid forms a bright violet colored complex, and this bright violet colored complex, it has a lambda max of 530 nanometers. So you can see the shift in the lambda max from 237 nanometers to 530 nanometers on treating salicylic acid with ferric chloride. So when you treat salicylic acid with ferric chloride, a complex is formed, a colored complex is formed with a greater lambda max, that is 530 nanometers, and thereby you can carry out. So here you can do two types of analysis. One is identification. So you can identify the salicylic acid based on the color that is formed, complex color that is formed, on treating with ferrichloride reagent, and the lambda max, so it absorbs, the colored complex absorbs at 530 nanometers. So CHROMOGEN, it can be utilized both for qualitative analysis as well as for quantitative analysis. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.